So in this lecture, we want to look at some problems that came in our previous examination, our UTME exam, concerning electrolysis. In the first part of our lecture on electrolysis, we did the introductory part. So if you have not seen the video, you can go down to check that particular video. We did the introduction to the electrolysis. We explained the concept. Then we are told there that there are three events that always occur during electrolysis, and one of them we said, number one, we said that there will be ionization. Then we now said there will be migration towards the electrodes, and thirdly we now said there will be discharge of ions. So during the discharge of ion, what happens? Like, how do the ions get discharged? This was, I told you guys in the lecture that this part of the work was studied quantitatively by a man that we call Michael Faraday, and he gave us two empirical statements that we call Faraday's laws of electrolysis. So in this part two of the electrolysis, the third thing that we didn't explain in the first part of the lecture is discharge of ion. So when we say discharge of ion, I told you guys then that if I have an electrolytic setup whereby I have a long and short arm like this of my current, remember, current will leave the longer arm that we call the positive, then direction of movement of electron will be conventionally opposite. And then we connected this conductor, then we connect it to maybe like your spoon, like your iron spoon at home, or any metallic spoon that you have. So then this part will be the negative part. So this is your negative rod, and this is your positive rod. And this rod, they will conduct electricity with the aid of free mobile ion, free mobile electron, because they are metallic conductor. Then we insert those conductors into a container where we pour our electrolyte. So remember, we have discussed the electrolyte fully in the first lecture. Then remember that almost all the electrons that are on this rod, they will pack themselves and migrate to this negative one. So there are excess of negative electrons here, while here there is deficit of electron at this electrode. And I told you that electrodes are metallic conductors that bring currents in and out of our electrolyte. This our electrolyte, let's say for instance we are using molten sodium chloride. In that lecture I told you that the word molten means there is no water. So that means that here everything that I have in this electrolyte, they are all sodium ion and chloride ion, and remember that there are billions of them. So what happened during the migration? The positive ions will migrate to a negative electrode, and the negative ions will migrate to the positive electrode. And this migration, upon getting to where they are going to, remember that all the sodium will migrate here. And when they come here, what happened? They don't like the charge on their head again, so they wish they could lose it. The only way for them to lose it is because there are excess electrons here, they will collect electron. So the sodium Na plus now has collected electron. I will use plus to show that it has gained one electron, and what happened is that it becomes sodium metal with no charge. In this case, this guy has gone from plus to 0, and if you go from plus to 0, that is reduction. So if you check one of our videos, you will see that. I also explained in the previous video that the sodium that we have here, this sodium ion that moved here, it gives name to this electrode because these positive ions are cat ions. Therefore, the rod they moved to, we now call the name of this electrode, we call it cathode. So that means that at the cathode, what happens at the cathode is that people used to gain electron at the cathode, because the reason why the positive are moving there is to go and gain electron. And when you gain electrons, you are reduced. So that means reduction occur at the cathode, and this is how we write the equation that occur there. Then if you look at the other side, the other electrode that we have, because the electrode is a positively charged electrode, what happens is that the negative ions will migrate there. So the chloride ion in this example will move to this electrode, and upon getting to this electrode, what happens is that they will lose the electron they have on their head to the electrode. Upon losing the electron, that means we remove electron away from them, and they also become neutral. They are discharged. So in that case, I can now write that my chloride ion, it has lost electron. Maybe I should use minus electron. We have removed the electron from his head, or the electrode has helped him to remove the electron, and the guy is now becoming Cl, neutral. But in chemistry, we don't used to write this minus something like this. Instead of me writing minus electron here, I would rather carry that minus here. It will become plus on this side, so I can cancel this electron away and write it here as plus electron. Because some people are wondering that how do I know if I am to write plus here or I am to write the plus on this side. So here, the reason why we wrote the plus here was that this metal gained electron. The reason why we could not write the plus here was that we removed from him, so we write the plus at the other side. So if you look at what we have, the chloride ion here is minus, but on this side is now neutral or zero. From negative to zero, is that a decrease or an increase? If you watch the lecture on redox reaction, you will see that this is an increase from negative to zero. So therefore, this is oxidation. Where does this occur? Remember that the name of these electrodes are gotten based on the ion that move to them. The ion that comes here, they are sodium ion, and therefore sodium ion is a cation. So I call this electrode, I call it a cathode, and this is the event that occur at that cathode. While the electrode that I have here, the ion that come there, they are anions. So therefore, I call it an anode. So, and at the anode, they tend to drop electron, or we tend to remove electron. So therefore, they are oxidized. Why at the cathode, they are what? They are reduced. So if we check that, this is a simple illustration of what happened. But if you look at what has happened here, here I have been able to successfully use one electron. And here as well, I have been able to remove one electron. The electrons that we are removing from here, we don't just remove them for free. They are work that are done in this cell, this DC. Imagine that you have bought electricity with your money, like prepaid meter, for instance. Let's say you have bought 200 charges. Your 200 charges that you have bought, if you want to produce one sodium, you have already used one out of these 200. Then if you need to produce 2 sodium, you will need 2 electrons. So the number of the metals, the element that you are producing, it needs a particular amount of electron. So that means that if I am having 200 charges here and I want to continue producing sodium, 1 electron will produce 1 mole of sodium. You can see clearly that the sodium is standing all by itself. But look at, in the case of chlorine, when I used 1 electron, what did I get? I got a chlorine atom, Cl. You know, in chemistry, some elements cannot stand this way because they are diatomic gases. So because of that, before I can get 1 mole of sodium that I'm having here, you can see that 1 mole of sodium is having 2 atoms. But 1 mole of chlorine is having 2 atoms of chlorine. But if you look at what I have here, 1 mole of sodium is still 1 atom of sodium. So that means that if I want to produce 1 mole of chlorine, I am going to need 2 electrons before I can do that. So with the aid of 2 electrons, I will get 1 chlorine, because 1 atom of chlorine will need 1 electron. Remember, okay? If you now want to get 3 moles of chlorine, what do you think is going to happen? If I need 3 moles of chlorine, this is how we are going to write that. Right? That means we need 6 atoms of chlorine. For me to get 3 moles of chlorine, I will be in need of 6 charges to do that. 6 electrons. And if I use 6 electrons here to get this, out of the 200, the number of electrons I have are reducing. Remember, I must use money to buy my electricity or the charges that I'm using. So it means that the currency that we are spending in electricity, the kind of things that we need in electricity, in electrolysis, they are actually electrons. In order to make this to be very, very clear, you can see clearly that if I want to prepare sodium or chlorine here, let's start with sodium. If I want to prepare 200 moles of sodium, you can see that clearly I am going to be in need of 200 electrons. Why? 1 electron will be needed for a sodium. Look at the chlorine as well. If I want to get 200 moles of chlorine, you can see that it's not possible, because the 200 electrons that I have now, what they can do is, remember, one molecule of chlorine is 2 naira. It's like 2 units of whatever currency I call. But what I call the currency, I said electron. So if one molecule of chlorine will use 2 electrons, so if I am having 200 electrons, I can only get 100 moles of chlorine. Let's take another example again. Let's say we are thinking about calcium ion. Let's say I want to prepare 1 mole of calcium ion. For this calcium ion to become neutral, I will need to add 2 electrons to this guy. Look at the head, 2 plus. That means that if I want 4 moles of calcium ion, I am going to, for every 1 mole of calcium ion, I will need 2 electrons. And when I need 4 moles of calcium ion, if I need 4 moles of calcium ion, I will be in need of 8 electrons. So therefore, you can see that different elements, the number of charges that we need to put in them will tell us a lot. For instance, let's look at oxygen as another element. If I need 1 mole of oxygen gas is a diatomic gas written as O2. But remember, oxygen is a group 6 element, 2, 6. It will gain how many electrons? 2. So it is O2 minus. In order for me to get 1 atom of oxygen, how many electrons will I need to carry away from the head of this person? 2 electrons. So that means in order for me to get O, I will need 2 electrons. What about getting O2? How many electrons will you need? You will need 4 electrons. So 1 mole of oxygen will need 4 electrons. Let's still use another example. Let's say we are working with aluminium. Aluminium is Al3 plus. How? Atomic number 13, and that's 2,8, 3. So the guy is going to lose 3 electrons. So that means in this case the guy has lost 3 electrons. So it must gain those 3 electrons back. That means for me to get 1 mole of aluminium, I must have 3 electrons to be spent. Then what about if I need 3 moles of aluminium? How many electrons will I need? 3 electrons for 1 mole, 6 electrons for 2 mole, and 9 electrons for 3 moles. All these things made Michael Faraday to now say everything happening here in just 2 empirical statements, and they are called Faraday's laws of electrolysis. So in the first law of electrolysis, Faraday told us that the mass of the element that we deposit, because once the element become neutral, they are now deposited and we can see them live. If they are gases, they are evolved. So that means that there are 2 things. We can liberate the gas, or we can evolve the gas, or we can deposit the element. So he now said that the mass of the element deposited during electrolysis, the mass of the element deposited, that the mass of the element deposited is directly proportional to the quantity of charge passing through the electrolyte. It means that if I want to discharge sodium here, and I pass all these my 200 charges through this electrolyte, I am going to get 200 moles of sodium. What about if I pass 400? I'll get 400. If I pass 600, I'll get 600. What about if I want to prepare chlorine and I pass 200 charges? I'm going to get 100 moles of chlorine. I hope you remember why. Because 1 mole of chlorine takes 2 electrons. So therefore, I'm going to get 100. What about if I pass more electricity? The more the electricity I pass, the more the mass of the element deposited. So mathematically, the mass of the element deposited is proportional to the quantity of charge passing through the electrolyte. So if you remember, according to Andrew Ampere, that current can be defined as the quantity of charge passing through a conductor in a unit time. So from here, my quantity of charge equals to current times time. So if I bring that in the formula here, my mass is going to be equals to if I introduce a constant and I call it Z, my mass is going to be equals to ZQ, where Q is IT. So the mass equals to ZIT. The Z is a constant that we call electrochemical equivalent. I is current and T is time, where M is the mass of the element deposited. This is quite simple, and we mostly come across this particular first law in our physics. But in the case of chemistry exam, we have to think about the other law that we call second law of electrolysis. The second law, the basic idea of second law has been what we have been describing since morning. You can see that if I have an electrolyte and that my electrolyte contains the element sodium ion or a salt of sodium, and I have another electrolyte that consists of the element of magnesium, and I have another electrolyte that contains the element of calcium, and I have another electrolyte that contains the salt of aluminium 3+. You can see clearly from what we wrote here that all these elements, the amount of electron that will satisfy them depends, can you see, on the charges that is on their head. So if I want to discharge 1 mole of this guy of sodium, I need just 1 electron. But is that the case here? No. If I want to discharge 1 mole of this magnesium, I need 2 electrons. If I want to discharge 1 mole of calcium, I also need 2 electrons. The same thing will happen here. Why? Because the major factor is what they carry on their head, the charges. And because they have the same charges, even if they are not the same elements, the same amount will be discharged here. But if you look at the case that we have here, if I want to discharge 1 mole of this aluminium, I will need 3 electrons. So 3 electrons for 1 mole here, then 2 electrons for 1 mole here, then 2 electrons as well for 1 mole here. But what about in the case here? 1 electron for 1 mole. Let's now make an assumption. Let us try to pass 21 charges through them. So you know, of course, I can pass the same electricity through different electrolytes if I arrange them in series. I can pass the same amount of electricity across all of them. So if they are arranged in series and I want to pass the same electricity through them, all these 4 solutions, I am passing, let's say, 21 charges through them. If I am passing 21 charges across all these 4 solutions, the 21 charges here will give me 21 moles here. But will this 21 give me 21 moles here? No, because 1 mole here will need 2 electrons. So here